So one of the great challenges in cell therapy is the ability to track cells following transplantation, and the existing approaches are suboptimal. So one of the existing approaches is using optical imaging. The problem is that using fluorescence, for example, you have limitations in the depth of penetration, so you can really only see cells that are a few millimeters below the surface of skin, for example. The other challenge is with radionucleotides that actually they rapidly decay, and so and the resolution is quite low. So typically you can only use radionucleotides to image cells on the order of a day or two following transplantation. And so there's really a big unmet need to develop better imaging tools and modalities to track cells, especially in the clinic. And so we were very interested in using MRI. And so there's been a number of groups who have been using iron oxide nanoparticles to track cells following transplantation. MRI offers significant resolution on the order of tens to hundreds of microns. But one of the challenges with MRI is that the iron oxide nanoparticles, although they can be internalized into cells, they're rapidly exocytosed, so the cells essentially spit them into the extracellular environment. And as cells divide, these particles become very dilute, and it's difficult to track cells for long periods of time. And so we were very interested in developing an approach that would try to address these challenges. And so what we did is, in previous work, we had discovered that 1 to 2 micron size particles could remain in cells for long periods of time and were not readily exocytosed. And so as the cell divides, we still have these large particles inside the cells. And so what we did is we took degradable PLGA, which is standard suture material, microparticles that were 1 to 2 microns, and we doped them with iron oxide nanoparticles. And that allowed us to enhance the amount of iron that we could get per cell. And then these large particles were retained in the cells for long periods of time. And so we were able to significantly enhance the duration at which we could track cells, so on the order of weeks. So we went from days to being able to track cells for weeks. We were also able to alter the contrast in terms of the when we apply a pulse of radio frequency pulse, how quickly the electrons relax. So the PLGA had a unique ability to change this relaxation time, which significantly enhanced contrast. So this approach, we think, could be really useful for tracking cells, especially in the clinic, because not only can we enhance the retention of the iron in the cell for long periods of time that would be useful for longitudinal studies, but also by altering how the electrons respond to a pulse of radio frequency and how they relax, we actually were able to get significant enhancement in contrast. And so not only are you able to track the cells for longer, we believe that this will offer enhanced contrast during this time period.